Okay, so number 10 and 30. If you guys missed this in class, you better pause it because I'm moving on to number 44. 44's final answer is 4.5. And then 52 for people who didn't get it in class. 56, you might need to kind of zoom in and pause. There's C and D. There's number 62. And as I was saying the rest of the class, remember the table I gave you? A couple on the table. The nasty one in the book, but you don't need to memorize it. You don't need to fully understand it. That's kind of beyond where we want to be. Awesome, you got 44, right? Okay, section 6.2, law of cosines. Law of cosines system. Some of it's hanging off, so let's figure it a little bit. Okay, number 2 should have been law of sines. Number 10, little c is 11.0. Guys, remember you should have 3 decimal places. You can check my pretending if you didn't have 2. 11.06. Angle B is 23.13. Angle A is 51.87. Hopefully you had 3 decimal places. Number 34. Angle B is 89.62 something or 63. Angle A is 57 point something. Angle C is 32 point something. Number 36. They ended up using, since it was since it was 2 angles, they said law of sines is way easier. So they used law of sines to find the third angle and mix it up and solve. I think some of these were like, hey, use whatever formula is easier, right? So angle A was 161, side B was 118, side C was 9.9. And once again, they like law of sines because there were 2 angles. Law of sines is always easier to do that. Number 38. There's just a plug and chug. Did you run this formula? Final answer is 399.47. And I think these are the last 2, right? Can you zoom in on 56 just a little bit? 56 was a bit of a struggle. They were actually having you solve an ambiguous case, which you can do with law of cosines, it's just not fun. In that you have this x inside the formula because you don't know what x is. You didn't know that other side that you really wanted to know. So it's kind of awkward. You actually ended up getting, wait a minute, what's this big old thing look like? Quadratic formula. Well, how did they know it? Because x was squared, x was single, and x was common. So your A coefficient is 1, your B coefficient is -3 cosine, your C coefficient is 46.75. So they went ahead and plugged into the quadratic formula. X equals negative, equals 9 squared, equals 9 squared. So all over. Got it. They plugged and chugged it, but you didn't know theta either. Which, I mean, they did this weird simplifying stuff. You actually didn't have to. You could have just plugged this whole nastiness with alpha y equals the big old fraction you would have graphed it, and then to find the maximum, all you gotta do is use your max feature, and the maximum is either here on the left or here on the right. You could have found the max is at y equals 8. And last but not least, number 66. SSS should have been law of cosines. AAS, 2 angles, law of sines. SSA, ambiguous case, law of sines. And SAS, 2 sides, law of cosines. Any quick questions on the odds that we didn't go over? On 61460? 25 on this one. Anything else besides number 25? Yeah, yeah. The first one. We go open up real quick. So anything else besides 51 on 6.1 and 25 on 6.2? No. As we do that, you guys get your notes close. Let's go ahead and get those 25. somewhere on this page. Let's now wait. Let's try 16 first. Okay, we'll come back to 51. Number 25 was one of those nasty fill in the chart thingamabobs, right? I believe it wasn't that nasty. Come on, my geometers. Complete the table by solving the parallelogram. Shown in the figure, the lengths of the diagonals are given by C and D. Okay, so, get my pen. For number 25, we know A is 5. We know B is 8. And we know beta, this entire thing, is 45. This is the right problem, right? We're looking for C and for D and for B hypothumb. How do you figure out what's supposed to be said? 5. Either way, we're trying to find this guy, and we're trying to find each of these guys. Now, C and D are both, I think it says the entire diagonal. So D is this entire shebang. Why is that not a bad thing? Why do we like including this whole side? We have 5, an angle, and 8. Yeah, law of cosines, right? Law of cosines. You can use side, angle, side, and be able to find the opposite side. Caleb.
It's 5.
It's 5?
No, 5.
Oh, 5. Yes. Well, I wasn't exactly sure. I'm hopeful. I'm grateful. So, guys, you've gone ahead and done what? B squared is equal to 5 squared plus 8 squared minus 2 times 5 times 8 cosine of 45. Someone, anyone, who figured out D and who wasn't? And while we think of that, well, hold on. Once you find D, how on earth are we supposed to find C? Diagonals of the parallelogram are known to be. So therefore, D and C should be equal. What'd you get for D, Maggie? 12.065. What'd you get for C? Double checking the parallelogram. This guy's instantly out of circles. Oh, yeah, you're right. I was thinking rectangles. Sorry. Rectangle. It's not. They're not congruent. Diagonals of a rectangle are congruent. Parallelogram, it's squished. Remember? It's squished to one side. Silly geometry. So wait a minute. Oh, how do we find C? Wait. Sides of a parallelogram are congruent. So hold on. We can use the 5 and the 8, but we need to figure out the included angle for this other triangle in order to figure out C. So hold on. How do we figure out who phi is? Parallelogram, the sides are what? Parallel. So we have a transversal going through. Kiddos, angles on the same side of the interior of a transversal
Congruent.
aren't congruent. That's alternate interior angles are congruent. On the same side, they're supplementary. They add up to be 180. So therefore, if I know the bottom one is 45, then question, what would the top one be? 135. So you can go ahead and fill in 5 to be 135. Is that going to change things when I go to the law of cosine if I use 8 and 5 and 135? Yes. So we can go ahead and throw 135 into our 5 and go ahead and then throw it. I'm just going to use Maddie's 5 point something 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 for C. There you go. Do 12 point something 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 for D. 5 point something 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 for Q. And then 5 is 135. Maybe a second. Because it's on the SAT. You can't have forget geometry. Geometry's not the SAT sometimes. Anyways. Alright, Caleb, let's try one more time. Let's see. Maybe? Yes. Just doesn't like that page. Give me that badly. Alright, maybe we'll try again tomorrow and I'll just try to reopen it. Sad time. Let's come on back to notes. That's calculus. That's not going to help us much. Where's my calculus? Here comes. Yesterday we started section 6.3 vectors. Oh no, we left 2 blanks, guys. How on earth are we supposed to be able to figure that out? You know what else we didn't do? We didn't get inspiration for figuring out vectors. Question, what do the arrows show on the picture? Are the people literally going up and then down? You don't have to put it in your notes, it's okay, we're just checking it out real fast. What do these arrows show? Are they literally going up and then they're going down, all in this one little moment of the roller coaster ride? It's exactly how the forces are pulling, and exactly, well, to be honest, I don't really like this picture completely, because they show all of these forces as being equal, and that's not necessarily true. We saw yesterday the length as meaning. It doesn't go on forever like the rays in geometry. So I don't like that as much. Let me go look at one more picture with a roller coaster that I think is a bit more accurate. In this one over here to the side, we do see the little people in the car side. We see the little people in the car, and we see this, what we call a normal force, which is perpendicular to the track, going up, and then we see the force of gravity pulling down. Do you guys notice how the normal is longer than gravity? That means it's stronger than gravity. So the length actually does have a meaning. But these ones right here that I just showed you, they're kind of working against each other. Now they are working on one object, the people in the car, but we're working against each other. If we were to show like a vector diagram, we would go ahead and put them together, which we're going to learn today, how to put some vectors together in order to find the net force. Someone help me out. What does net force mean? Well, what does net profit mean? The total, like the complete picture, put everything together, and what's the result? So the net force is saying, okay, if you have gravity working down, the force normal working up, what do you feel in the car? You feel that net force pulling up a little bit. Which is kind of weird, I know. Now, if you're over here on the side of a loop, right, you can still see over here, you have the normal force pulling this way, you have gravity is pulling that way, and then you say, what's the overall force that you probably feel? Like, what's the combined effect? Because you guys don't probably feel 2 different forces acting on you, right? You feel one combined force. But what do you notice about the difference between the arrows drawn on the left and the arrows drawn on the right? We make a triangle on the right, that's true. And then on the left, do you guys see how the arrows are? This is normal force, that's what they made. Gravity is what they made green. What's the difference between how the arrows are pointing on the left and how the arrows are pointing on the right? Yeah, on the left, they're kind of working against each other or opposite, and on the right, they've been translated in order to show them being put together. Being put together is one goes into, the head of one goes into the tail of the other. We're going to talk more about that soon. But then we are able to see the combined effect or the net force. And at the top, well, the top is kind of easy. We'll skip the third one, which is kind of like the second one. But when we go to the top of the loop, just to spot an example of that. What forces do we have? Well, they're all kind of pulling here down. The question was, yeah, the hardest is helping. And centrifugal motion is helping. Wait, centrifugal motion. So you guys can take physics. Anyway, nope, no physics. But this one's already oriented. We put the one going head to tail into the other one, so the one flows into the other, and then we get the combined net force, which everybody's pulling down here on the top. These other ones, they're kind of pulling different directions to get the net force. They're kind of pulling different directions and put them together. So, to inspire you with roller coasters, I figured we should probably watch a random roller coaster scene from a fairly popular old hill. I'm just having roller coasters. And maybe some of you guys will figure out why I chose Despicable Me. Ricky, go get the lights. So, what does that mean about me? I know this is horrible. That's just
Okay.
Please! Oh, please! Please!
question. Why did it show despicable me? No need blood suffering. Hold on. Not yet. Why did it choose despicable me? Out of all the roller coaster scenes and all the videos.
It's exaggerated.
Okay, it's exaggerated, number one. Number two, you gotta put yourself in the different seats that I showed. But also, don't we have something else we're supposed to fill in?
Oh, vector.
Why did I choose despicable me?
Vectors the villain. Oh.
Vector's the villain. I wonder if they'll help us out.
I'm applying for a new film go by the name of Vector. It's a mathematical quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Alright, oh yes! Fires live piranhas ever seen them before. Now you have my do a demonstration. Oh, ah! Sometimes
Okay, so hopefully we're not going to be quite as silly as he is. However, you guys should know how to fill in those lines now, right? What are we going to do? Direction and magnitude. Go for it. You want to say, oh yeah, you can. Maybe minus the hip thrust. All right, so direction and magnitude. Question: how do we see direction in the line? Well, the arrow. He says arrow, but it's only going one direction. Okay, focus. No more sugar for you. All right. I know. No, don't give it away. Put it under your desk. Nope. Put it under your desk. You don't need any more sugar. Question: look at that arrow. One-sided arrow, I should say. Where do you see the direction? Okay, so the arrow, that helps, right? That shows direction, but what else shows direction?
A straight line.
Not exactly. The rotation of the straight line. Ooh, the rotation, which we could say is the theta. Right? If you know number one, the rotation, and number two, the arrow, you know the direction it's headed, or it's pulling, or it's pushing, or it's speeding away at. Right? So direction, we can see that with theta. Let me go ahead and quickly, up here, show it. But not just the theta, also the arrow, we need both pieces. Because couldn't it also, or couldn't it instead be headed this direction, and it would be completely opposite? So, be careful. You need the arrow and the angle of rotation. This one is in standard position. There is another one called a bearing, but we'll talk about that. Magnitude. Okay, you guys live in California. You should know magnitude. What's magnitude talking about? Okay, yes, it's applied to earthquakes, but like the force of something. But, hold on, isn't force just one thing that a vector can measure? Let's not just use force, magnitude. The amount, or the greatness, and in notation it's going to be double lines with the name vector, which could be V or W or U or G or whatever. But it's going to be the name of the vector, which down below is V. Remember our notation, that little arrow, and I like putting just one little end on it, not both ends. Or I should say one little tail on it, not both tails. Most technically the head. Anyway, to make it different than a ray for geometry. You also need two little lines. The magnitude is literally, if I was to put the two little lines here, it's the actual length, which could be measured in many different things, but it's the actual length itself. And that's why I showed you guys the example of one illustration where I just showed all these vectors where they were the exact same length. But that's not very practical. This one doesn't show exact same lengths, but the rest of them do, and that's not very practical. It's more practical when we have ones of differing lengths, like you saw in that example. All right, let's keep going. So what do we know so far? Vector, line segment. that has both direction and magnitude. We know that we can talk about a vector with a little one-sided arrow and a lowercase letter. That's what we saw yesterday with vector v. The book's going to make it a bold letter, but we're not going to do that. We have to put the little arrow on top. And we also saw that we can talk about it as the initial point, which we call the tail, and then the terminal point, which we call the head. Unlike geometry, you can't put these just in any order. You have to do initial, then final. Okay? Let's keep going. Magnitude. Let's talk about him for a little bit. Direction is just an angle. We've dealt with angles a lot, especially with trigonometry. But magnitude, okay. The length denotes the amount of force or the speed of velocity, or the actual distance. It's the how muchness. It's the how muchness of the quantity. It's the amount, it's the greatness, it's the magnitude. If you ever take physics, you're going to learn about velocity. Velocity is how fast and in what direction, whereas speed is just the magnitude. Speed is just the amount, which is why on your speedometer in your car, you don't have positive and negative numbers, you only have what? Positive numbers, because it's just how fast you're going, it doesn't care in what direction. Magnitude, just the how much is. Notation for magnitude can be the double lines with the initial point, terminal point, which can also be seen as, let's see, no I don't. Let's just say it can also be seen as the double lines of the lowercase letter, which we saw on the last page. It can be seen either way, both of them are synonymous. One of them shows the initial terminal, one of them just shows the name. To have equal vectors, that's the bottom part. To have equal vectors, they have to have both the same magnitude and also the same direction. They have to have the same magnitude and the same direction, which means not only do they have to be parallel, but they also have to have the arrows going the same way, right? So two things with direction, they have to have the exact same angle of rotation. Wait a minute, but they're all over the place. Well, in physics, we learned that you can actually, wherever something is, you can kind of put his own little Cartesian plane with him. And if we were to give each of these little guys a little Cartesian plane, guys, what would be the same about each of their little angles of rotation? Yeah, they're going to be congruent with each other, right? So all the little angles of rotation, even though the vectors are in different places, we can still say they're equal in their angle because they're going to have the exact same rotation from what? From the positive x-axis. Well, there's not just an x-axis. How about due east? Does that make sense? They're all headed the same way. Think navigation. Wouldn't due east be straight to the right?
Yeah.
So we could say they have the same
Bearing.
bearing of an angle northeast. Northeast, east of north. And they also have the same direction, they also have to have the same magnitude, the same length. So let's go ahead and test that out and see if we know how to determine whether or not vectors are equal. Both pieces, the magnitude and direction have to be the same. Alright, kiddos. How could you prove to me that these vectors are equivalent? Okay, distance formula, that's one thing. And maybe the slope. Because the distance formula will tell me the length, right? We can test the two lengths, aka the two magnitudes. And then the slope, won't that maybe tell me something about their angle of rotation? We want to know about that angle, we want to know about that angle. So, let's go ahead and call this theta u, just so that we know whose theta it is. We'll call this one theta v. This one, the length could be the magnitude of v. Remember, put a little arrow on top. You're not writing in bold. You can't just pretend that you are. And the magnitude of u. That's what we have to find. So, magnitude of v. How does the distance formula work? I know it's a square root, but now what? Let's start with u. He's actually easier. Some of you have good ideas. use that. Some of you actually remember the formula, and that's good. Well, let's start with you. We want to know his hypotenuse. Wait, what? Why do you say hypotenuse? Couldn't I make it a triangle if I wanted to? I've done that with trig stuff before, right? Question, looking at that vector, he has a terminal point of 3, 2, an initial point of 0, 0. What does that mean his horizontal side of the vector? How about his vertical side? 2. So we can say, all right, x2, 3, minus x1, 0, which ends up being 3 squared, plus y2, which is 2, minus y1, which is 0, which ends up being 2 squared. Remember, the distance formula is just the Pythagorean theorem. That was from first semester, week 1. The distance formula is just the Pythagorean theorem. Subtract the x's, you get the horizontal. Subtract the y's, you get the vertical. Square root. And what's the magnitude of u, guys? Root 13. Good. How do I find v using the same or a similar process? We could make a triangle if we want. And couldn't we also use the initial terminal points to help us? Okay. So then, how do we know the horizontal? Good. Subtract each of the x's, right? And then how do we know the vertical? Subtract each of the y's. And we end up with 4 minus 1 is 3. 4 minus 2 is 2. Does it end up being the same thing as down below? Absolutely. Positive. So far, looking good. We have magnitude of v being rad 13. We have magnitude of u being rad 13. So root 13. Now we need to think about the angles. So we're going to go ahead and think about theta of vector v and theta of vector u. Now some of you guys mentioned, hey, the direction. Okay, we can think about the slopes. And you're right, but let's talk about why. First of all, do they both have arrows headed the same, seemingly the same direction? Okay, so that's a good sign. If one was going the opposite direction, we have to say they're not equal. They're headed the same way in the sense of up and to the right or northeast. Angle. Kiddos, if we have a right triangle, how do we find the angle? Let's start with maybe triangle for vector u. We could subtract from 90 if we look at the other side was. We're not sure what the other side is. But we have opposite and adjacent. And it's a right triangle. We could do sine over cosine, or it's an easier way. Opposite over adjacent is Toa. Who's T? I know, but who is T? Tangent! Thank you. He's tangent, right? Can't I just do tangent inverse of 2/3? Did you forget right triangles so quickly?
Yes.
After 2 sections of chapter 6. Coca-Cola. You can take opposite over adjacent and say, hey, he's tangent to somebody. Hey kiddos, what did you figure out about the opposite and adjacent of this guy? We did 4 minus 1 for the horizontal, 4 minus 2 for the vertical. Who's our opposite and adjacent of him? Still 2 over 3. Oh, do we even need our calculators to talk about the relationship of these two? Oh, because to get an angle, remember, we start with tangent of theta equals. Yeah. And just in case others of you had the same question, tangent equals opposite over adjacent. If we want to get theta alone, we have to go ahead and get rid of tangent using, well, inverse. Okay? Okay, let's go back to what I was showing up here, the double arrow. What's the relationship between these two guys without even going to our calculator? They're the same. So we can say equal magnitudes, y check yes. Equal directions, y check yes. So therefore, what's our overall conclusion? They are equal. They are equivalent. Equivalent is spelled equivalent right there. I'd rather. I said to myself my first one. Done. Yeah. about vectors. Don't worry, guys. We're not teaching an entire physics course. We're just pre the rest of math, and that includes pre-physics. Component form. Okay. So we just talked about how we can take a vector whose initial point, let me go ahead and show them this way, whose initial point, now, normally guys we show x's and y's, but just for sake of physics, let's just call this R1 and R2. I know it's weird. We'll see why. R1 and R2, like R's x and R's y for the initial point. And then for S, let's just do S1, S2. They are x's and y's, they are. But just for sake of illustration, let's go ahead and see the point separately. If we wanted to show the vector using its points, we could write this whole paragraph about how we have an initial point at R1, R2, and a terminal point at S1, S2, and the arrow is pointed towards the S. But that doesn't sound fun if there's a shortcut mathematical way of doing it, and here's the shortcut mathematical way of doing it. The shortcut mathematical way of doing it says, what if you were to start at 0, 0, and you would want to show an equivalent vector? Well, to show an equivalent vector, we would need to know how far over to go and how far down to go. You guys remember how we found how far over in the last example? For I think V was the one who was kind of out there away from the origin, right? How do we figure out how far over? Subtracted the, do you remember? Yeah, for the horizontal component, we had to subtract the x terms. So we did 4 minus 1. So in this example, we subtracted the x's. Let's go ahead and show it with the formula. We can go ahead and say, let's do R2, sorry, not R2, S1 minus R1. It's always the terminal point minus the initial point, the end minus the beginning. S1 minus R1 will give us the distance over S1 minus R1. And then we're going to put a comma, and then we're going to do S2 minus R2. We're basically just doing change in y's and change in x's. This will be S2 minus R2. The end minus the beginning. Now, in this form, there's also something else special that closes this in that lets us know it has to do with vectors. We're going to call them side carets. Caret, think of like the exponent button that you do to raise something to a weird power, like 5 to the 5th. You can use that little caret button in your calculator. These are called side carets. And we can call this the component form. And if we know the component form, or if we can find a component form using the initial point and the terminal point, then we can use Pythagorean theorem every time that you saw us do on the other page, where we did horizontal change, sorry, that needs to be an R1. The horizontal change squared plus the vertical change squared. Now the formulas are actually a little bit harder than just what we get to do in application. But component form, what that's talking about is these little side brackets where we show the horizontal change and the vertical change. And if we know that, then we're able to go over the horizontal, we're able to go down the vertical, and we're able to show, exactly, show an equal vector in a new position. So let's check out the example down below. There's an example down below. It's on the next page. Okay, two quick little like, these are special guys. A zero vector is a vector with, hopefully you guys can figure this one out. A zero vector is a vector that doesn't go anywhere. So we call him 0, 0. He starts at 0 and he ends at 0 and he doesn't go anywhere else. He doesn't go over at all, he doesn't go down at all, he's just at the origin. Zero vector has no length. Unit vector has a length of a magnitude of 1. Components will be a little bit different depending on what's going on. But a unit vector is going to have a length of 1. You could also technically say, if you wanted, a zero vector is going to have a magnitude or a length of 0. I guess you could say that too. He doesn't go anywhere. He has a length of 0. Kind of boring. Let's go check out an example with these components. So how would we take this vector? Do you guys see the arrow? It's kind of small. Where is it? Now hold on. Double check what you're writing. In the directions, find the component form and magnitude of vector v, but you're not writing in bold. What do you have to put above him? Yeah, when you're writing that guy, you better put a little arrow on top. You're not writing in bold. Same thing when you do directions for your homework or you put answers. Don't check it with calc chat. You're not writing in bold. You have to have little arrows on top of it. So how do we find vector v? Side caret. Side caret. Plug in what? Negative 1 minus 2. What else do we plug in? Yeah. Just take the terminal point, which is this guy, right? The head. And subtract the tail, or the initial point. Head minus tail. So we end up with a final component form of negative 3, positive 2. And what does that show? If we were at 0, 0, we would need to go 3 to the left and 2 up. And we can also think of it as 2 and negative 3 in order to go from the beginning to the end. Does that make sense what we're doing? And why on earth is that component form helpful for finding what we need to find next, which is the magnitude of v? Now we can square root. Can't we just do Pythagorean theorem since horizontal and vertical are always going to be at 90 degrees to each other? North, south, and east, west are always at 90 degrees to each other. How do we find the magnitude? How do we find the hypotenuse? Why using Pythagorean, of course. What are you guys doing? Exactly. To be honest, in physics, or whenever you're working with vectors, it's super nice to have a component form because they make the math easy of whatever you're supposed to be doing. Negative 3 squared is 9, 9 and 4 is 13. That's a popular number today. Root 13. So component form, one more time. Those are the side brackets, side carets. The side carets showing the horizontal change or displacement and the vertical change or displacement. And from that, we can say, that's just the right triangle, no big deal. We can find the magnitude using Pythagorean theorem. Hi, cool kids, you can start homework, but we're still taking another day or two on this. We'll see. I have homework due on Friday. Start it, you don't finish it. Bye, guys.